Hello, in this video we're looking at MEI FP2, the June 2010 paper question 2, which is on complex numbers. Read through the question first. We're given an expression for z and asked to express z to the n plus 1 over z to the n and z to the n minus 1 over z to the n in simplified trigonometric form. These are fairly standard results, so you should be reasonably confident about reproducing these. You don't need to memorise the results, but you do need to know how to set about finding them. We're then asked to use that to find the constants A, B and C in that identity. We must use the first part of the question, otherwise we won't get all the marks. Part B is quite independent of Part A. We're asked to find the fourth roots of minus 9j and to write them in that form, noting that r is bigger than 0 and theta is between 0 and 2 pi, so theta isn't negative. We're then asked to illustrate the roots on an argand diagram, so one diagram. And then we've got to label those points in order of increasing theta, p, q, r and s, and look at the midpoints of the sides of that quadrilateral. Those points represent the fourth roots of another complex number, w. And we've got to find the modulus and argument of w and mark that point on our argand diagram. So there's a lot to do there. We need to make sure we don't miss any bits out. Okay. Given that z equals cos theta plus j sine theta, so start here. I've got z to the n plus 1 over z to the n is cos theta plus j sine theta to the n plus cos theta plus j sine theta to the minus n. Using de Moivre's theorem, that's cos n theta plus j sine n theta plus cos of minus n theta plus j sine minus n theta. That's cos of n theta plus j sine n theta. Cos of minus n theta is cos of n theta. And j sine of minus n theta is minus j sine of n theta. So the two terms with j cancel out and I'm left with 2 cos n theta. Then I've got to do z to the n minus 1 over z to the n. And I don't need to redo the working I've done before. I can just note that that's cos n theta plus j sine n theta minus cos of n theta minus j sine n theta. This time the cos terms cancel and I get 2j sine n theta. Then I've got to find A, B and C in that expression. So I've got sine to the 5 theta. Okay. I'm going to start with z minus 1 over z to the 5 because I know that z minus 1 over z is 2j sine theta. So I'm going to be able to get my sine to the 5 out of that. Multiply that out using the binomial z to the 5 minus 5 z to the 4 times 1 over z plus 10 z cubed times 1 over z squared minus 10 z squared times 1 over z cubed plus 5z times 1 over z to the 4 minus 1 over z to the 5. Collecting bits together, that's 10z, and this is 10 times 1 over z, so I've got 10z minus 1 over z, and then this is 5z cubed, and that is 5 times 1 over z cubed, so that's minus 5z z cubed minus 1 over z cubed, and then z to the 5 minus 1 over z to the 5. The bit on the left from part 1 is 2j sine theta all to the power 5. Okay. 2j sine theta to the 5. 2 to the 5 is 32. J to the 5 is j. Sine theta to the 5. Sine to the 5 theta. Z minus 1 over z is 2j sine theta. Z cubed minus 1 over z cubed is 2j sine 3 theta, and z to the 5 minus 1 over z to the 5 is 2j sine 5 theta. So all of those terms have a j in it, so I can divide through by j. 32 sine to the 5 theta is 20 sine theta minus 10 sine 3 theta plus 2 sine 5 theta, and then dividing through by 32. 20 over 32 is 5/8. 10 over 32 is 5/16. And 2 over 32 is 1/16. So A is 5/8, B is minus 5/16, and C is 1/16. For part B, the fourth roots of minus 9j. Well, these are easiest to find if I've got minus 9j in r e to the j theta form. So it's 9e to the 3 over 2 pi j. We can get that quite simply from a quick sketch. Minus 9j is down here, so the angle is 3 pi over 2 and the modulus is 9. So the fourth roots of that are r e to the theta j, where r is the fourth root of 9. That's the square root of 3. Our first value of theta is 3 pi over 2 divided by 4, which is 3 pi over 8. And the other values are a quarter of the way round, so 2k pi over 4 for different values of k. So for k equals 0, 1, 2 or 3. So theta is 3/8 pi, 7 pi over 8, 11 pi over 8, or 15 pi over 8. And our roots in the form that we're required to write them, root 3 e to the 3 pi over 8 j, root 3 e to the j 7 pi over 8, root 3 e to the j 11 pi over 8, and root 3 e to the j 15 pi over 8. Now we need to mark these on a diagram. So our first point is at 3 pi over 8, so it's going to be about there, and they are going to be evenly spaced around the origin, making a square. So the other points are there and there. So that's all I need to do for the first bit, but it then talks about the midpoints of the sides PQRS. So let's actually draw the square in. And label it P, Q, R and S. And look at one of those midpoints. We'll call that point M. So this length here is √3, and this angle here is pi/4. Okay. The length PS, so the side of my square, is going to be the square root of 3 plus 3, using Pythagoras, which is √6, and therefore the length OM is going to be √6/2, half the length of a side, bearing in mind that's a square. The argument of that fourth root, well, the angle all the way around to P was 3 pi/8. The argument of this root is 3 pi/8 minus that pi/4. So this angle here is 3 pi/8, and to find this angle here, which is the one I want, I need to take off pi/4. So that gives me an answer of pi/8. So W has argument 4 times that. Remember, that's the fourth root of W. So 4 times pi/8, which is pi/2, and its modulus is going to be √6/2 to the power 4, which is 6 squared, 36/2 to the 4, 16, which is 9/4. So W has argument pi/2, so it's on the imaginary axis, and modulus 9/4, so W is going to be up there somewhere. Let's just check we've done everything in that question. We've got the points representing the roots, we've labelled them P, Q, R and S. The midpoints of the sides represent the fourth roots of complex number W. We've found the modulus and argument of W, and we've marked the point representing W on the Argand diagram. So we have completed that question. Okay, let's go back and see how the mark scheme works for this question. For part A, there is simply one mark for both of those expressions. They are standard results that you should be familiar with and able to reproduce very quickly. Finding A, B and C in the identity, there is a method mark for expanding z minus 1 over z to the 5. And then another method mark for putting sine of theta, 3 theta and 5 theta and so on. And an accuracy mark for the right hand side there. And then an accuracy mark with follow through from the previous part for division by 32j to get your values of A, B and C. For part B, there's a method mark for, just a straightforward mark for getting the modulus of the fourth root. There's a mark for getting the argument of the first of those roots. There's a method mark for noting that you need to add this on, and that can be implied by at least 2 correct further values. And then an accuracy mark for getting the 4 correct angles. The mark scheme does in fact allow you arguments in the range minus pi to pi, even though the question specifically asks for them between 0 and 2 pi. They're quite lenient on that. You've then got to draw your diagram, and there's a method mark for getting the vertices of a square with centre 0, or for getting at least 3 of the points correct, or for getting 4 points, 1 in each quadrant. And then there's an accuracy mark for having that square correct. Then we get to the bit which is a little bit more generous with marks. There's a method mark for working out the length OM, and another mark for getting the argument of that point as pi over 8. There's then a method mark for working out that the argument of W is the previous argument times 4, and that you need to do the modulus to the power 4. And then an accuracy mark for actually doing those and getting them both correct. And then there's a mark for plotting that on the imaginary axis somewhere above P. If you want to find videos of other equations on this unit or on other units, please visit the Further Mathematics Support Programme's website. Goodbye.